In this video, we're going to talk about the fundamental theorem of algebra. So first thing we're going to answer is, what is the fundamental theorem of algebra? And the fundamental theorem of algebra says an n-degree polynomial has n zeros. That's simply what it says. Now, what does that mean? All right, let's actually translate it into some words that might make some sense. So things that we have worked with. We have worked with quadratics. Okay. Quadratics are second degree polynomials. All right, so they're second degree functions. So what does this mean? It means that a quadratic has two zeros. All right. Now, we've talked about zeros in a couple of ways. We've talked about zeros as what makes the function equal, what values make the function equal to zero. You can also think about x-intercepts. Now, some of you might be looking at this saying, wait a minute, I know we've done problems that only have one x-intercept for a quadratic. And so what you want to be careful about is when we talk about this definition, we have to pay attention to something called that multiplicity that we've been talking about. So for example, right, there are three different ways that quadratics can be graphed depending on your zeros. Now, I'm going to draw these graphs all as concave up just to keep them all the same. It doesn't particularly matter. You could draw them all concave down too. So you could have a quadratic that clearly crosses the x-axis twice. This has two zeros. All right, two real zeros. Now, you can also have a quadratic that just whoops, hold on, let me actually make it touch. Just touches the x-axis. And this particular quadratic would have one zero, but it would have multiplicity of 2. So this 1 0, because it has multiplicity of 2, actually counts as both zeros. Now, the goofy one that we're not going to talk too much about for right now is what happens when you have a quadratic function that just doesn't touch the x-axis. So you might look at this and say, well, it has no zeros. What actually ends up happening is it has two imaginary zeros. So imaginary values exist. We use them all the time in math. You just can't graph them on the real number system. So when you have a quadratic that does something like this, it's just imaginary zeros. It's not a big deal, all right? But it still has two zeros. They're just imaginary zeros. So that's what would happen if you had a quadratic. You can do the same idea for a cubic function. A cubic function is a third degree function, so it should have 3 zeros, all right? Now, what we're going to do when we put it in practice is we're going to look and say, does a function match a graph? Does a graph match a function? You know, what can we do to see how this fundamental theorem of algebra can be applied? All right. So example number 1, given the graph below, could the graph be modeled by a quadratic function? All right. So we just talked about quadratic functions, and we just mentioned that a quadratic function is a second degree function. Okay. If it's second degree, that means it has two zeros. But the problem is this particular curve has 1, 2, 3 zeros. So no, this particular function cannot be modeled. This particular graph cannot be modeled by a quadratic function. Okay, so let's see if we can put this all in some words here. All right, no, the graph has 3 x-intercepts and a quadratic function is only, that is horrible, hold on a second, only, there we go, second degree. A second degree function has exactly 2 zeros, not 3. Okay, so yeah, there's no way that that particular function, that a quadratic function could model that graph. It doesn't make any sense. Okay, so the answer is no. But make sure that when you're explaining it that you're using the mathematical vocabulary. So the graph has 3 x-intercepts, a quadratic function is only second degree, and a second degree function has exactly 2 roots, not 3. All right, so example number 2, given the graph below, could the graph be modeled by the function negative parentheses x minus 3 times the quantity x plus 5 times the quantity x minus 7? Explain your answer using mathematical vocabulary. All right, so we have 1, 2, 3 linear functions being multiplied together. So when we've got 3 linear functions, this is a cubic function, okay? And it is third degree, okay? So a third degree polynomial has 3 roots. So if I look at the graph, I cross the x-axis once, twice, 3 times. Yes, this graph could model, could be modeled by that function. So yes, the graph could be modeled, whoops, by the f of x function, since, oops, there's an n in there, since, hold on a second, I write horribly right now. All right, let's try this again. Since it is a third degree function. Actually, I'll put polynomial. Okay, so absolutely that graph could be modeled by that function. It's a cubic function. You go through the graph 3 times. Yep, we're good. All right, let's slide on down to example number 3. Based on the fundamental theorem of algebra, sketch a graph that could model a cubic function. Well, cubic function means third degree. So we want 3 zeros. So mark 3 points on the x-axis, right? There's our 3 zeros. And you are just going to draw a graph that goes through those 3. Except apparently in my case, you missed one completely. Let's try that again. Oh, much better. There we go. All right. So that's a sketch that could model a cubic. There's lots of them. There's an infinite number of them that could work. All right. All right. Based on the fundamental theorem of algebra, sketch a graph that could model a 6th degree function. Well, 6th degree function means I need 6 zeros. So 1, 2, 3, 4, 5, 6. So let's see what we got here. So we'll start, I don't know, positive this time. There we go. All right. So we've got 1, 2, 3, 4, 5, 6 zeros. That is absolutely a function that could model a 6th degree, or a graph that could model a 6th degree function. Okay. Based on the fundamental theorem of algebra, sketch a graph that could not model a quadratic function. Okay, so a quadratic function we know is second degree. Well, if it's second degree, it means it has to have exactly 2 zeros. Well, if you graph anything that has more than 2 zeros, that means it wouldn't model a quadratic. So let's say I draw something that has 4 zeros. Definitely not a quadratic, all right? And last but not least, based on the fundamental theorem of algebra, sketch a graph that could not model a fourth degree function. So a fourth degree function would have 4 zeros. Let's go ahead and say that I'm going to make, I don't know, 5 zeros. All right. So when we look at this, it is not possible for a fourth degree function to have 1, 2, 3, 4, 5 zeros. It's just not possible. Okay. Now, one of the things we're going to talk about in the next unit is it actually is possible for a fourth degree function to have graphically less than 4 zeros, because again, you could get into multiplicity and some other things that happen there. So the best way to show that these graphs don't work is to pick a value that's higher than the given degree. So in example 5, it was a quadratic function. I made it really simple and said, all right, well, a quadratic function cannot have 4 zeros. In example 6, it said, again, a fourth degree function. Well, I'm going to go with something larger than that, and so I went with 5 zeros. All right, please let me know if you have any questions or concerns about the fundamental theorem of algebra and how to get some of these examples that could work and things that can't work.